Hi everyone, welcome back. In this video, we will discuss measured numbers and significant figures. The learning goal for this video is to be able to identify a number as measured or exact, and to be able to determine the number of significant figures in a measured number. So let's look at this ruler. Length is measured by observing the marked lines at the end of the ruler. The last digit in your measurement is an estimate, and we will call it the estimated digit. And it is obtained by visually dividing the space between the marked lines. And so, for example, we can see that the marked lines are 0, 1, 2, 3, 4, 5 centimeters. And that I know for sure that this piece of wood is at least 4 centimeters. That is known. But I could estimate that it looks like it's close to 4.4 centimeters. You may have said it looks like it's 4.5. This last digit here is called the estimated digit. And when you're using instruments that are not digital, you will need to report your measurements with one estimated digit. So measured numbers are the numbers obtained when you measure a quantity such as your height, weight, or temperature. Once again, to write a measured number, observe the numerical values of the marked lines, and then estimate the value of the number between the marks. And the estimated number is the final number in your measured number, just like what we did in the previous example. Now I encourage you to pause the video and determine the measured values given each ruler, and then come back and check your work with me. All right, let's see what you got. So we did A already. Like I said, I had said it was 4.4 centimeters. You may have said 4.5. That last number is estimated, so that's going to vary from person to person. Let's look at B with this ruler here. Now notice how there's other increments. So this ruler is more precise than the first and last ruler. And I need to determine, well, what do those little lines mean? I can see that there's 9 of them, which makes me think that this is divided into 10. For example, this is 4.1, 0.2, 0.3, 0.4, 4.5, 4.6, 4.7, 4.8, 4.9, 5. So the minor increments are every 0.1 centimeters. So if I zoom in a little closer, I can see the ruler is somewhere between 4.5 and 4.6 centimeters. So I'm going to write that I know for sure it's at least 4.5 centimeters because this digit is known, but I'm going to estimate where it's at between the two. And I think it's a little over halfway. So I'm going to say that my estimated digit is 4.57. 7 is the estimated digit. Now you may have said 4.55 or 4.56. It's okay to have some fluctuation with the estimated digit from person to person. Now with C, we know that it's at least 3 centimeters. Now this one, if we zoom in, looks like it's right on the line. However, we need to include another 0. We need to include an estimated digit because 3 is known and it could be anywhere between 3 to 4. And so just like with part A, the 10th place was the estimated digit. We need to include a value for the 10th place, even though it's estimated. So for me, I'm like, ooh, it's right on the line. This is 3.0 centimeters. However, you may have looked at it and thought it was a little past the line and put 3.1. Now, if there's a difference in the estimated digits, that's okay. But the more important thing is that we did write a number in the 10th place because we must include that estimated digit. If you just wrote 3 centimeters without the 0, then it would not be the correct way to report this measured value. In a measured number, the significant figures, which I will abbreviate as SF, are all the digits, including the estimated digit. So it does include the estimated digit. Significant figures are used to represent the amount of error associated with the measurement. Are all non-zero digits and zeros between digits. Are not zeros that act as placeholders before digits. Are zeros at the end of a decimal number. So I'm going to go through the rules for significant figures. And this is a core chemistry skill to master, counting significant figures. And so I encourage you to have this table close by when you're practicing your problem set, because it is important to have this become second nature to you, to be able to look at any measured value and determine the number of significant figures easily. At first, you will need to rely heavily on this table, all the guidelines, but with more practice, you'll become more proficient at it and will need this table less and less. So let's walk through this. A number is a significant figure if it is not a 0. So any non-zero numbers, and I will underline those, are considered significant. So 4.5 has 2 significant figures. This measured value here has 5 significant figures. A number is significant if it is a 0 between non-zero digits. I call these sandwiched zeros. So they will always be significant. So for example, 205 meters has 3 significant figures. 5.008 kilograms has 4 significant figures. So we count sandwiched zeros as significant. A number is a significant figure if it is a 0 at the end of a decimal number. So what I always tell students is to look if there's a decimal. And if there are any zeros after the decimal, they are considered significant. And even in this case, after this non-zero number, this would be considered significant. So 50 point liters is 2 sig figs. 25.0 degrees Celsius is 3 significant figures. And 16.00 would be 4 significant figures. So those trailing zeros after a decimal do count as significant. A number is a significant figure if it is in the coefficient of a number written in scientific notation. So all numbers, including zeros, are significant in the coefficient of scientific notation. So 4.8 times 10 to the 5th meters is 2 significant figures. 5.70 times 10 to the negative 3rd grams has 3 significant figures. A 0 is not significant if it is at the beginning of a decimal number. So once again, if it is preceding the first non-zero number. So we start counting at the first non-zero number when we count sig figs. So even though there's a decimal here, those preceding zeros do not count. This measurement only has 1 significant figure. And this measurement of 0.075 only has 2 significant figures. So we do not count preceding zeros before any non-zero number. A 0 is not significant if it's used as a placeholder in a large number without a decimal point. So if there's no decimal point, then trailing zeros do not count. So in this case, this measurement is only 2 significant figures, and this second measurement is only 3 significant figures. And that is because there's no decimal point, and these zeros are only used as placeholders. For example, if all I wrote is 85 meters, that's very different than writing 850,000 meters. I need those zeros to indicate how large this value is. When one or more zeros in a large number are significant, they are shown clearly by writing the number in scientific notation. So for example, let's say we have the measurement 300 meters, but only the first zero is significant. Then it's easiest to write your measurement in scientific notation. So for example, because the coefficient indicates the number of significant figures, so we only want 2 sig figs because only the first zero is significant. The second zero is a placeholder. Then we write the coefficient with the non-zero number followed by a decimal point, and then include that zero there to indicate 2 significant figures, times 10 to the what? Good, to the second meters. If we were to report this value just as is, it indicates only 1 significant figure because trailing zeros with no decimal point do not count. But if we know our measurement should have 2 significant figures because it will indicate the precision of the measuring tool we are using, then writing in scientific notation is a way to get around that by including only 2 sig figs in the coefficient, because both of these numbers count as significant since it's in the coefficient. So remember that zeros at the end of a large standard numbers without decimal points are not significant. So if you wanted to write this value in scientific notation indicating only 1 significant figure, you would write 4 times 10 to the what? Good, to the 5th grams. Make sure you always include units if they're there. So this helps us to indicate only 1 significant figure in scientific notation. What about this second measurement? If we only wanted to write it with 2 significant figures, how would you write that? Good, so you would write 8.5 times 10 to the 5th meters. Excellent. Remember that zeros preceding the first non-zero number are not significant. So this value only has one significant figure, and to write that in scientific notation, you would write what? 4 times 10 to the, excellent, -4 seconds. What about the second measurement? To two significant figures, it would be 4.6 times 10 to the negative. Let's see here. We have 1, 2, 3, 4, 5, 6 to the -6 grams. There we go. All right, pause the video, and when you come back, check your work with me. All right, so I hope you identified the significant and non-significant zeros in each of the following numbers and you wrote them in correct scientific notation. So let's check your work. Okay, so first thing is how many significant figures we have. I like to underline them. So it looks like I have 1, let me do that, 1, 2, 3, 4. So this 0 is significant because there's a decimal point, and trailing zeros with a decimal point are significant, but the preceding zeros are not. So we want to report this answer to 4 significant figures when we write it in scientific notation. So we would write 2.650 to indicate 4 significant figures times 10 to the -3. Good. And then that's in meters. Okay, so for this one, first determining the significant figures, I'm going to start with the first non-zero number. 3, 4, 5, that sandwich 0 counts. So there are how many significant figures? There are 5. So when we write this in scientific notation, we're going to have to write all of them. 4.3026. Remember, with scientific notation, you always have the decimal after the first non-zero number. The coefficient always needs to be between 1 and 10. And so this is 4.3026 times 10 to the 1 grams. Excellent. And the last one here, let's go ahead and underline our significant figures. So 1, 2, 3, 4, but we don't count those zeros because there's no decimal. So these trailing zeros do not count. So there are 4 significant figures. And we would write that as 1.044 times 10 to the 6 liters. And let's just go ahead and write the number of significant figures for each of them. This was also 4 sig figs and 5 sig figs here. Remember, this is a core chemistry skill, so the more practice, the easier it'll become, and you're going to utilize this core chemistry skill throughout the rest of our time together. So we've been discussing measured numbers, but there are also exact numbers. Exact numbers are not measured and do not have a limited number of significant figures. It's important to recognize if you have an exact number, because it's not used to find the number of significant figures in a calculated answer. Exact numbers are obtained maybe by counting. So for example, if I baked 8 cookies, that's an exact number. Or if I needed 6 eggs to make a cake, that's an exact number. Exact numbers are also definitions that compare two units. So for example, there are 4 cups in 1 quart. Those are exact numbers. And exact numbers could be definitions in the same measuring system. For example, 1,000 grams in 1 kilogram. This is the metric system here, and these are considered exact numbers. So we do not take into account exact numbers when we determine the number of significant figures in a calculated answer. Here are some more examples of exact numbers. Once again, there's some defined equalities. For example, there are 16 ounces in a pound. Comparing, the English system, here, the units, they are exact because we're comparing them within the same system, just like in the metric system as well. Or once again, just counting, the number of capsules or the baseballs, like that's exact number. All right, so here's another study check. Please pause the video and then come back and check your work with me. All right, so let's identify the numbers below as measured or exact and give the number of significant figures in each measured number. All right, 3 coins. How did you identify that one? Good, it is an exact number. And so therefore exact numbers, because we can count them there's 3 coins exactly, there's no significant figures. The diameter of a circle is 7.902 centimeters. Yeah, this is a measured number. And a lot of times I always tell students to identify a measured number is if you need a tool to get that number. So for example, the diameter of a circle, I'm thinking I would need a ruler to measure that, right? And so that gives me a clue that this is a measurement, a measured value, and therefore has significant figures. How many did you determine? Good, there are 4 significant figures. 60 minutes equals 1 hour. Excellent, this is an exact number because it's a definition from within the same system of measuring time. So no significant figures there. All right, thank you for watching. And as always, email me with any questions.